Let us recall what we have did in the previous lecture. In the previous lecture, we have defined the conversion sequence. In a matrix space. So if X is a matrix space, and if you want to say the sequence which is in X, it's called conversion in X. If for every greater than 0, there exists n0 belongs to n, such that distance between xn and x is less than epsilon for every n greater than or equal to n0. That means after n0, a distance between these 2 points or xn and x will be small as much as you can. Then we have proved that the limit of sequence is unique. Then we have defined the Cauchy sequence. So Cauchy sequence is a sequence for which every epsilon greater than 0 and 0 belongs to n such that d of xn and xm is less than epsilon for every n greater than or equal to n0. N and m greater than or equal to n0 means that after n0, the distance between every pair of points in this sequence xn will be tending to 0. We have proved that every conversion sequence is a Cauchy sequence in a matrix space. But the converse is not true. We have seen the example of that, the example which I have given you, that if you consider ux is open interval 0 to close 1, and we define xn as 1 by n, then this sequence is Cauchy sequence and it is converged to 0, but 0 is not in this. So I can say that this xn is not Cauchy, not convergent in the x. So we can say that Cauchy sequence will not be implies conversion sequence in general. So due to that, which extra condition we can add here into the Cauchy sequence, so it will become convergent. So for that, we have learned one result. It's known as every Cauchy sequence has convergent subsequence. Then the sequence is convergent. That means the sequence is Cauchy. If it has convergent subsequence, then that sequence will be a Cauchy sequence. So that thing we have learned, and with that we have defined what is a complete matrix space. So what is a complete matrix space? It is a matrix space in which every Cauchy sequence is convergent. That space is called a complete matrix space. We have seen the examples of a complete matrix space. We have seen that R is a complete, closed interval 0, 1 is complete, C is a complete, C0, 1 with infinitive norm, D infinitive, where D infinitive is fxy, where supremum of fx minus g of x belongs to 0, 1 is there, then C0, 1 is also complete. We have seen that X with the discrete matrix, any space we consider with the discrete matrix is also complete. So we have discussed lots of examples and related things we have discussed in the previous lecture. Now, in this lecture, we will talk about the two things. The first one is a limit of a sequence, and the second one is a limit point of a set. The first question is arise whether these two things are same. That means if I have a sequence and if this sequence is convergent, we can say that it is converged to a limit x. And whatever the set we construct from this xn, let's say that set is x1, x2 up to xn and so on. So the question is whether a limit point of this set will be x. That means, can I say that the limit of a sequence is nothing but the limit point of a sequence? What is your idea says about it? What is your conclusion says about this? Have you understood the question? If I have a sequence, if the sequence is convergent, we can say that it is converged to a limit x. So x is the limit of this sequence, we can say. Now there is a limit point of x. Limit, if I have a sequence, we can write down this is as a set. Now this is x1 point, x2 point. So this set contains these points. Now what are the limit points of this set? So the limit point of this set is may or may not be x, or it is always x. That is my question. Whether it is always x or may not be x. So what is your answer to this question? For example, if I have a sequence 1 by n, then we know that this sequence 1 by n converges to 0 as n tends to infinity. That means I can say that 0 is the limit of this sequence. In the similar manner, if I define a sequence, a point of this sequence, that is 1, 1 by 2, 1 by 3 up to so on. If this is the sequence if I define, then what is the limit point of this sequence? What are the limit points of this sequence, which you already discussed in the previous one of the lecture? A limit point of this sequence is 0, because when you consider a neighborhood of 0, this neighborhood of any neighborhood of 0 contains a point of this type. So that's why 0 is a limit point of the set, and 0 is a limit of the sequence. That means in this case, limit point and the limit will be a same. Is this situation is always be there? That my question is. Is this always possible? The answer is no. It is not always possible. For example, if I consider a sequence 1, constant sequence 1, for n running from 1 to infinity, and we know that this is a constant sequence, then it will converge to 1. So the 1 is a limit point, limit of this sequence. Okay, so I can say 1 is a limit of a sequence singleton 1. Now if I define a set 1 now, set 1 means it only contains x1 is 1, x2 is 1 and so on. So it is only contains 1 point. Now what is the limit point of this singleton set x or singleton set 1? That means if I consider 1 and if neighborhood of that 1, and if I remove the center point from this, intersection of this neighborhood, any neighborhood of that with singleton 1, except that point, will be always empty. So I can say that 1 is not a limit point of the singleton 1. In fact, there is no limit point of this set. So in this case, a limit point and the limit is different. Okay, so let us write that is as a remark here. So we can write down by this argument which we have explained, we can write that a sequence may have limit but cannot have a limit point. Like in this example, it have a limit but it has no limit point. The set of points of a sequence may have a limit point but cannot have a limit. This is possible. Construct the example of such type. Now, my objective or my concern is in which situation the limit point and the limit will be a same. So under which situation, under which condition, we always get a limit point and the limit will be same. So for that, we will have a next result. So it says that if you have a conversion sequence and which that conversion sequence has infinitely many distinct points, then the sequence of a limit of a sequence and the limit point of the set of points of a sequence will be the same. Like in this example, here this sequence contains infinitely many different points. But this sequence does not contain infinitely many distinct points, only contains one. So that's why, so that is the result that we have, and the statement of the result we can write in this manner, that if convergent sequence in a metric space has infinitely many distinct points, then prove that its limit point is a limit, or its limit is limit point of the set of points of a sequence. Proof of this. So what is this says? If the sequence which is convergent and it has the infinitely many distinct points in that sequence, if the sequence contains infinitely many distinct points, then the limit and the limit point of the set of points of the sequence is the same. So the same statement I may also can state in this manner. So let xn be a sequence with infinitely many distinct points in X and Xn converges to X as n tends to infinity. Then prove that the set x1, x2 up to so on has limit point x. So this is the same way. This is in notation. Either you can write this statement or the statement. Both of them is true. Now let's take the proof of this statement. Let X be a metric space and Xn be a convergent sequence with infinitely many distinct points in X with Xn converges to X as n tends to infinity. Now we need to prove that this X is a limit point of set of points of the sequence. So we shall prove that X is a limit point of set of points of the sequence Xn. So we go by contradiction. Suppose not. Suppose not. That means this X is not a limit point of the set of points of this sequence. So if it is not a limit point, then what we can say? By definition of limit point, what is the definition of a limit point says? For every r greater than 0, SR of X minus X intersection with A is non-empty. So this is the definition of limit point. If you want to say that X is a limit point of A. So here this X is not a limit point of this set of points. So the negation of this statement gives you for some r greater than 0. So you can write for some r greater than 0, or there exists r greater than 0 such that SR of X minus X intersection with x1, x2 up to so on will be empty. Okay, so this is the things we got. But what is given to us is Xn converges to X. So by definition of this convergent sequence, but given that Xn is converged to X, that means for given epsilon greater than 0, there exists n0 belongs to n. We say that Xn is belongs to S epsilon of X by definition of this open sphere definition of convergent sequence. We can say that for every n greater than or equal to n0. Let us take, since this statement is true for every epsilon, so that's why I am taking epsilon is equal to r. So that means this xn is belongs to S R of x for every n greater than or equal to n0. If I call this is the statement 2 and this one is the statement 1. So what is this meaning of this statement 1? It says that this point, so this a sphere having the intersection with this set of points will be empty. And this statement says that after this n0, that means xn0, xn0 plus 1, up to so on, all of these points are in this. So how many points this SR of x contains, which intersection with this is empty? Okay, so only the points left, they are x1, x2 up to xn 0. All other points xn 0 minus 1, xn 0 is in this space, in this set, xn 0 plus 1 is in this set, and so on. So that means this set of points only have the finitely number of distinct points. Otherwise, this both statement will not be possible. Statement 1 and statement 2. So therefore, what we can say from 1 and 2, we say that there are finitely many distinct points in Xn, but which is a contradiction with our given condition, because it says that the sequence will must have the infinitely many distinct points. Why we got of this contradiction? Because we assume that this is not a limit point. So which is a contradiction with our supposition. Therefore, x is a limit point of this sequence x1, sorry, this set x1, x2 up to so on. So ultimately what we can say, and this is very important results, we are going to use this result in the next result, which is very much important. So we need to remember what is the statement is, that a convergence sequence is there and which having the infinitely many distinct points, then the limit point of that sequence will be same as limit of the sequence. Now we have to discuss the next example. For example, when I say R is a complete and C01 is also complete, but open 0 close 1 is not complete. So what that makes difference between these two sets, so that this will be a not complete, but this will be complete. Both of them are a subset of some space, which is a complete space. So what is the argument, or what is the leg in this space, or what is the property of this set? So it will not be a complete, but what will be the property here? It will contain, so it will be a complete matrix space. So with this observation, we can state this theorem, that let X be a complete metric space and Y be a subspace of X. Then prove that Y is complete if and only Y is, you just observe that this side is a closed set, but this side is not a closed set. So that gives you this argument that Y is complete if and only if Y is closed. So this result is actually gives you or tells you that if you have some subspace which is a subspace of a complete metric space, then in that space a closeness is equivalent to completeness. So some set is complete if and only if that set is a close. So let us try to prove this statement. Here our objective is to prove that we assume that Y is complete and we will prove that Y is closed. So suppose that Y is complete. So I want to prove that Y is closed. So it is sufficient to prove that every limit point of this Y will be in that, because that is the definition of a closed set. So we shall prove that every limit point of Y is in Y. So let us start with let Y, small y, be a limit point of Y. Since it is a limit point, as per the definition of a limit point, what we can say, for every r greater than 0, SR of Y minus Y intersection with Y is non-empty. This is the definition of this. And this statement is true for every R. So that means I can say for every n belongs to n, S 1 by n Y contains a point yn which is in Y. Because as per this, there has to be some common points in between these two for every R. Okay. So as per that argument, if I choose this R equal to 1 by n, and for every n, we will have some points which are in here. All the points are also here. Okay, so that's why there are some points in this set which are also in Y, and all those points we are considering, or we can saying that it is Yn. So therefore what we can have here, it is Yn is belongs to 1 upon S 1 upon Ny. But this will gives you Yn comma Y is less than 1 by n as per the definition of this neighborhood, and which will tends to 0 as n tends to infinity. So hence this Yn is converged to Y. So that means we can say that Yn is converged to Y in X. We don't know yet where is this Y point is. This Y is in X. So that's why I have written Y in X. We have to prove that this limit, this sequence is in Y. But we have to prove that this limit should be in Y. Since it is a convergent in X and the sequence is in Yn, we definitely say that this Yn is a Cauchy sequence in Y. And since Y is complete, every Cauchy sequence will be convergent. So Yn is convergent in Y. But Yn is already converged to Y, and the limit of a sequence is always unique. So it should not be converged to some other point. It has to be converged to Y, and that Y has to be in Y. So therefore, we can say that Yn is converged to Y, and which is in Y. So that means, and the Y is the arbitrary points we have taken. So that means we have proved that every limit point of Y, it is in Y. So therefore, every limit point Y of Y is in Y. Therefore, Y is closed. Conversely, suppose that suppose that Y is closed. What to prove? Y is complete. So if I want to prove that Y is complete, I have to show that every Cauchy sequence in Y will be convergent in Y. So I have to start with let Yn be a Cauchy sequence in Y. And Y is a subset of X. So therefore, I can say that Yn is a Cauchy sequence in X also, because Y is a subset of X. But what is X? As per the argument, X is a complete metric space, and there is a Cauchy sequence in that complete metric space. So what we can say, this Cauchy sequence has to be convergent in X. So since X is complete, Yn is convergent in X. Let us say it converges to X, which is in X. Let's say Yn is converged to X, which is in X, as n tends to infinity. What is our objective? Our objective is to prove this X is in Y, because I want to prove that every Cauchy sequence has to be convergent in that, and Yn is already converged to this X. So we want to, or we shall show that we shall show that belongs to Y. Now there will be two possibilities are here. And we will use the previous result which we have discussed regarding the infinitely points and finitely many points. If this Yn has only finitely many points, many distinct points, then what is happened to X? So there is a sequence, and that sequence is converging to X, and that sequence contains only finitely many points. That means this X is repeating infinitely many times in that sequence, in that set, or in that sequence. So I can say that then X is that point which repeat infinitely many times. In Y. Okay, so Yn is actually a sequence in Y, and Yn is converging to X, and which will be repeating its infinity many times. So this will tells you that X is in Y. Now there is another possibility is that Yn has infinitely many distinct points. Instead of finitely many, we can have the Yn has infinitely many distinct points. Then what will happen? Then by previous result, what we can say that what was the previous result we have? If it has infinitely many distinct points, then the limit point and the limit is the same. And what is the limit of this sequence? The limit of this sequence is X. So I can say that X is a limit point of the set Y1, Y2 up to so on. But where is this set? This set is in Y, and Y is a closed set. So therefore this X is in Y, because it says that every limit point of a closed set should be in that set. So that means X is in Y. So which is our objective is to prove. So hence we can say that Y is complete. What we have proved is if it is closed, then it will be complete. So with this result, we have proved that closeness and the completeness is the same thing under the complete matrix space. Like you will have R, and if you want to say that R is complete, or we know that R is complete, and if you want to say that any subset of R, you want that it is a complete, then it has to be closed. Like closed interval 0, 1, we know that it is a closed set, so it will be complete. And this result is true for any complete matrix space.